some fundamental theorem of calculus and some indefinite integrals. Up here, guys, number one is an indefinite integral. I think the first thing you have to recognize is that this is x to the 3/2 dx. You guys agree? Because the square root's 1/2 power. And then the rule is the same. Add 1, divide by the new coefficient. So 3/2 plus 1 is 5/2. And we still have to have plus c. Listen, don't stop here. One more step, which is to write the 1 over 5/2 as that. And there's the answer today. And everybody, if you're not sure, take the derivative of that. 5/2 times 2/5 is 1. Take away 1 from 5/2 is 3/2. Oh, looky, looky. The derivative of my red box is my blue box. All right? Simple antiderivative. Sometimes on a test we will have indefinite, which means plus c, and sometimes we will put values here, which means you'll have to evaluate it. All right? And then you won't have plus c, but you will evaluate it between two values. Number two is a fundamental theorem of calculus. I have defined capital F of x as the area under the curve starting at 3, going to some letter x of this curve, which would be funky. We cannot do the antiderivative of x to the 7 minus 4, but we know that the fundamental theorem of calculus says just put the x in place of the x, and in this case it's really easy. It's just that, right? And if you think to yourself, well, Mr. Anderson, what about taking the times x? No, it'd be times 1, because what's the derivative of x? 1. And that's why on the next one, if I want, oh, I didn't say, if I wanted to find g prime of x on the next one, all right? First of all, what's the derivative of 7? 0. So we don't worry about the 7. And then what's the derivative of a? 0. So I don't worry about a because it doesn't matter. But now I have to plug the x cubed in. X cubed squared. Power rule. X cubed squared is x6 plus x cubed. But now I do have to multiply by something. The chain rule, right?
Times 3x.
3x squared. And that is the derivative of that function. Now, everybody, you can do this with a u substitution. I am not going to. If you put u in here as x cubed, you can prove the same thing. All right? It is always that way. All right, the next one up before we shut this video off, because we're already at 3 minutes, is I have a optimization problem. A rectangular prism needs a length that's twice the width and is 8 inches tall. If it must hold 576 cubic inches, what size box minimizes the material required? All right, so you see it doesn't say how fast does it change, and it says it wants to minimize. So the first thing I recommend is we have to do two things. I need a volume equation, and I'm going to need an surface area equation for that box. All right, so we have a couple things going on. Do you guys see that you can set a volume up here in this case of 8 LW? Everybody agree with that volume for that prism? And this time I said the volume has to be 576 cubic inches. So I think I have that equation going on right now. All right. To get surface area, I often draw the net, guys. I don't try to do anything else, all right? So I have these figures. And everybody, this is geometry time, right? And this is just some of the stuff we got to kind of know. We got WL, so when I go off here, all right, so do you guys see that figure? I just drew the 6 sides. I unfold the net of the surface area. And in black here, I'm going to write in the areas. 8L, WL, 8W, 8W, 8L, and WL. In black, right? I just took length times width of each rectangle. So the surface area of the whole figure, 8W and 8W is 16W, 8L and 8L is 16L, WL and WL is 2WL. All right, here we go. I want to optimize the surface area, all right? I want to optimize the surface area. And, well, actually, I didn't even need to put in that as twice the length and width, did I? I didn't even have to do that. So again, this is the problem when I'm trying to make problems up ahead of time. If I get rid of this, we could even do it this way. Right now, guys, to optimize the area right now, do you guys all agree? You could just replace the width with the length with 2W and get this equation to one variable. That's too easy. So let's get rid of that constraint. We'll drop that right out. We'll say it's 8 inches tall, all right? We'll say it's 8 inches tall. Everybody, I have to get to one variable, and I have this equation over here, 876 equals 8 times LW. What if I divide, there's 2 W's, 2 L's, I'll solve for L. I'll divide by 8W, and 576 divided by 8 is 72. Well, now I got length equals 72W. I can plug that into the black area equation. The volume was my constraint. I didn't need to double constrain it. And I get area equals, I have to get to one variable. You realize this is what we want to optimize. It has to be one variable. And I get area equals 16W plus 16 times 72 over W plus 2W times 72 over W. All right? I got to do some math here. I'm going to simplify this before I do the derivative. Take my calculator, take 16 times 72. And I get 1152, and I'll bring the W to the top, plus, how about just 144, right? The W's cancel. Now, everybody, I'm feeling real good about life at this point, believe it or not. Because now I can take the derivative of this, right? I've gotten it to one variable. I can now try to optimize it using our now. And optimization works on the idea that there are critical points, mins and maxes. So derivative of 16W, I think it's just 16. The derivative of this is negative 1152. W is a negative 2. All right. And what's the derivative of 144? 0. Set the derivative equal to 0. A prime equals 0. So I think I can do this. I get 0 equals this. Tell you what, I hate wasting time. So I bring that over. And I'm going to get 1150. I'm going to get W squared. When I solve this, you should be able to get to this. This is just algebra. W squared is 1152 divided by 16. I get W squared is 72. So guess what? I just figured out I got to take the square root, right? And I suppose you could make the argument that's plus or minus, but we all know that it has to be the positive answer. And I'm not going to go exact. I'm not going to do radicals here, even though you could. I'm just going to say W is 8.4853 inches. And everybody, inches. And everybody, if I asked, now it says what size box minimizes the materials. I know I gave you a height of 8 inches, right? We've calculated the width is 8.48. Well, yeah, to find out, well, don't we have a neat little equation for L right there? So it takes, and what you're going to find here, and it's not surprising, guys, think about it. W is the square root of 72. Guess what the other dimension is? 8.4853. What optimized the area? A square base. Or I would optimize the surface area. What minimized it? It optimized it to a minimum is a square. All right? And again, if I wanted to keep the phrase twice the width, the length was twice the width, then I could have got rid of the volume. You guys agree? And I could have done some things like that. Point is, you have to get to how many variables? You've got to get to one variable before you take the derivative, and it all has to be done in terms of that variable. All right, with optimization.